all the way, from the UV to the infrared. So I am going to show you two examples of, or discuss results of two projects that we have in which we use interference coatings. But the problems that we are trying to solve are very different. And one of these problems is, developing interference coatings for gravitational wave interferometers that operate at a wavelength of 1064 nanometers. And the other one is interference coatings for shear pulse amplification laser systems that operate at wavelength of 800 nanometers, 1030 nanometers. But these lasers, unlike the laser that is using the gravitational wave interferometer, produce pulses that are very short. So in other words, we are able to deposit all of the laser energy within an extremely short pulse. So we have extremely high intensity. So the way we grow our materials is using a technique that is called ion beam sputtering. An ion beam sputtering is a physical vapor deposition technique. So this is our instrument, and it's a commercial instrument. And I show you the high quality coatings that we can produce. In fact, this process allows us to create thin film layers that are very dense. They are almost like the bulk materials. And because they are very dense, they are very environmentally insensitive. Now we do a lot of characterization. So here is where the materials aspect come into place. The students that work in my group need to know how to grow materials, but they need to know how to characterize them. So we use different tools. We use X-ray diffraction to learn how, whether our materials are amorphous or they have any signs of crystallization. What you see here are traces of the X-ray diffraction pattern, the diffractogram of tantalum pentoxide that was grown with different conditions. And because we see these broad peaks, then we said, okay, this is a material that is amorphous. And we also carried out X-ray photoelectron spectroscopy because the X-ray photoelectron spectroscopy can actually tell us about the bonding environment. So here we are looking at the bonding environment of tantalum. Here we are looking at the bonding environment of the oxygen. And what we learned from these films is that tantalum is in its correct oxidation state, which is 5+, meaning that we are actually forming a film that is stoichiometric. So this is very important. We also carried out electron paramagnetic resonance experiments, and these electron paramagnetic resonance experiments allow us to detect different types of defects. And so I give an example here of silicon dioxide that was deposited from an oxide target. And so this is the electron paramagnetic resonance signal. If we deposit from a metal target, the signal changes drastically. And what this is telling us is that this type of defect is different than this one. In fact, this is an E' defect versus an oxygen interstitial. So another interest is to know what is the stress on the coatings that we grow. The physical vapor deposition method is one in which you can think of the material as a tetric material in the sense that we sputter a target that is a metal target, or it could be an oxide, and with an ion source. And this ion source, what it does is it produces a plume of material. But this material is a combination of, it could be atoms, single atoms, it could be molecules, or it could be clusters. So think that all of these components are falling onto a substrate. The process is a low temperature process, so there is very little diffusion. And as a result of that, whenever we generate this plume, whatever falls on the substrate stays on the substrate. There's very little mobility. As a result of that, the films have very high stress. So we measure the stress of the films using interferometry. And what you see here are results of interferometry in some of the coatings that we grow. This is, for example, in tantalum pentoxide, we measure 130 megapascals. In silicon dioxide, we measure 400 megapascals. The way that this interferometer works, in interferometry, what we measure is wavefront deformation. And this is the wavefront of one of these that a substrate of silica generates whenever is coated with one of these, either one of these materials. If you see such a large curvature, then for sure the stress is very high. So probably this is a film of silicon dioxide, in which the stress is about 400 megapascal. So we measure wavefront deformation, and then we use a formalism that was developed by a scientist or engineer named Stoney to relate the wavefront radius to the stress. And so by doing that, we have been, working on trying to reduce the stress in the films. And what we do is we essentially change the deposition conditions. So for example, in this case, we were bombarding the SiO2 with an oxygen plasma. And we see that there is a significant decrease in stress. So then we have to, design the coating. And so what we do is, for every material that we grow, we do ellipsometry and we measure the refractive index as a function of wavelength and the extinction coefficient. Generally, at 1 micron, all of these materials have an extinction coefficient of about 0. And so, what we will do is we will then design the coating, and then we will also measure the absorption loss. And we do this with a technique that is called photothermal common path interferometry. Now, typically, we can get coatings with approximately 30 parts per million absorption loss at 1 micron wavelength. But if we anneal the coatings, then the absorption loss decreases to about 10 parts per million. So, you will ask, well, is this good or bad? Well, it depends on the applications. For LIGO coatings, for the gravitational wave interferometers coating, this is not good enough. 10 parts per million is not good enough. So there has been a lot of efforts trying to reduce the absorption loss. And these coatings for gravitational wave interferometers have achieved 0.5 parts per million with annealing, which is record low. So now I am going to briefly discuss what are the problems that we are trying to solve in each of these 2 projects that we have in our group. So, and I will start by discussing interference coatings for gravitational wave interferometers. As I mentioned, these coatings are designed for a wavelength of 1064 nanometers. The interferometer has 2 arms that are 10 kilometers long or so. And at the end of these arms, there are mirrors, like you see here. and they are mounted like this. I mean, they are mounted, I mean, the mounting of these test masses, which are very large. This is about 24 centimeters in diameter, and this is about 30 centimeters long. So these are the mirrors in the interferometer. Now, the main issue in these interferometers is that they are designed to detect gravitational waves. Gravitational waves have an extremely small intensity. And as a result of that, then your instrument has to be very sensitive. Every time that a gravitational wave hits the interferometer, what it does is it changes the relative length of the arm in the arms of the interferometer. But this change is of the order of, is a strain of the order of 10 to the minus 21. So therefore, every component in this interferometer has to be designed to be stable to those type of levels. Now, and that's the reason why you see here the mirror is mounted. I mean, there has been a lot of technology, I mean, a large effort devoted to eliminate any instabilities from the mounting. But now there is one level of noise that we need to remove, and that comes from the noise that the coatings in these test masses generate. And this coating is associated with internal friction of the materials. So think that, I have my coating here, and is mounted on a substrate, a huge silicon dioxide substrate, and there is internal friction. Well, if there is internal friction, that means that the coating is going to be vibrating. It vibrates very little, but nevertheless, when a planar wavefront comes and impinges on the surface, then what will happen is that it will be distorted. And so then, we are talking about minute distortions, but nevertheless, I mean, if they are comparable to the amplitude of the gravitational waves, then that means that this noise will actually hide the signals from the gravitational waves. So this is what we are trying to control and eliminate or reduce: thermal noise or internal friction. And thermal noise is proportional to is a mechanical loss. So this is what we are going to measure. We are going to measure mechanical loss. Now in LIGO interferometers, the coatings that are used consist of stacks of tantalum pentoxide that is doped in which titanium impurities are added. And the low index material is silicon dioxide. Now, of these two materials, the one that has the lowest mechanical loss is silica. So we are working on the high index material to reduce mechanical loss. And today, the state-of-the-art coatings show that the high index layer, which is this tantalum doped with titanium, has a mechanical loss of 3 times 10 to the minus 4. So for the next generation of gravitational wave interferometers, then what we are looking at is decreasing the mechanical loss by a factor of 2. So in our group, we have the capability to grow materials in which we can dope, to grow mixture. So we can, for example, take tantalum pentoxide and add different other materials. For example, yttria or yttrium oxide, niobium pentoxide, hafnium dioxide, zinc oxide, and so on. And so we have tried that to understand what, whether by using other materials but titanium, which is the one that is used today, we can actually reduce mechanical loss. And what we have learned is that, as I am going to show you, is that there is a specific structural configuration that leads to lower mechanical loss. So here, what I showed are results of mechanical loss. We don't measure mechanical loss. We send, coated substrates to a colleague at Caltech, and where he measures mechanical loss. And the way that it is done is, imagine I have, this is my substrate, and then I come and I, touch here in a very controlled way, and then the substrate starts to oscillate, and we measure these oscillations, and then we analyze these oscillations to determine the mechanical loss. And so what you see here is loss angle, which is inversely proportional to mechanical loss, as for all the different alloys that we deposited. And what these results showed is that actually, when we add zinc, we can get a mechanical loss that is comparable to titanium. Both will have a mechanical loss of about 2.8 10 to the minus 4. So what we then do is we anneal the materials, and with annealing, what this plot shows is that the mechanical loss reduces. And the best value is, right here, is this one, is about 2.8 10 to the minus 4. So we were actually intrigued by what happens, in these two materials, zinc, when we add zinc and when we add titanium, what happens to the structural properties of the material, and why do we get a lower mechanical loss? So we conducted X-ray diffraction experiments, and what you see here are diffractograms of all of the different tantala alloys, tantala with alumina, with silicon, with titanium, and so on. And these are the two that achieve the lowest mechanical loss, which is 40% lower than that of tantalum pentoxide. And what we learned is that in both cases, and unlike what is observed with the other dopants, we actually form a new phase when we anneal the materials. And so this is unique to these two systems. On all the other systems, when the material crystallizes, we will see that one of the phases will crystallize. So for example, here we are seeing that on all cases, because tantalum pentoxide is the majority of the material, we have about 20% of the impurities or of the dopants into tantalum pentoxide, then tantalum pentoxide will crystallize at high temperature. And that's something that is guiding us, onto selecting the type of materials that we can use to to create or to realize low mechanical loss ternary alloys. We can also grow nanolaminates. And what you see here are high resolution transmission electron images that show nanolaminates of silicon dioxide and tantalum pentoxide. Each of these layers is nanometers thick. And here we have the same for silicon dioxide, tantalum pentoxide. And this is the same structure, anneal at 650 degrees. Then down here we have nanolaminates of titanium dioxide and tantalum pentoxide as deposited, and then when we anneal. And what we have learned, again, is that when we anneal, we observe a very different behavior. When we have silica, notice that annealing doesn't affect the nanolaminates, but when we have titanium, yes, there is a change because now this structure that originally was designed as a nanolaminate became a structure that in which now the interfaces are diffused. And this happens because there is mixing and homogenization of the titanium dioxide into the tantalum pentoxide with annealing. Interestingly, what we see is that whenever we have this mixing process, as we saw before, is when we get the lowest mechanical loss. And this is, in the case of the nanolaminates, we are seeing exactly the same behavior as in the mixture. Now, why do we want to grow all of these different structures? Is because there are theories that show that that try to explain the reduction of mechanical loss in ways that that look at affecting the near range, the nearest neighbors structures in the coatings. Remember, these materials are amorphous when we grow them. So there is, they don't have a long scale range as crystal material. So what did we learn from these experiments? Well, we learned that in mixtures, we obtain the lowest mechanical loss whenever in samples with a cation concentration of about 20%, and that we observe that whenever we anneal, there is the formation of a ternary phase. And this behavior is also observed in nanolaminates. So whenever we have diffusion, and whenever diffusion is thermodynamically favorable, then we can form other alloys, and it looks as if this is the condition that we need to realize low mechanical loss. So now I'm going to briefly cover the second topic of our work, which is understanding how we need to design interference coatings for ultra-high power lasers. So the geometry that is used to generate high energy ultra short pulse laser is called chirp pulse amplification, and it's schematically shown here. So we start with a seed, which is low energy and probably 50 femtosecond pulse duration. And then what we do is we go through through an expansor that will expand the beam. It will expand the pulse. Okay, so we do this with gratings. And so in order to expand an ultra short pulse laser, what I need to do is I need to gain in bandwidth. So this is exactly what I show here. And this all comes from Fourier analysis. You know from your signal processing that a short pulse in the time domain will be composed by a broad frequency spectrum in the frequency domain. And this is exactly the same in optics. So then what we do is we amplify in energy using laser amplifiers this pulse. And so we get this. We get a broad pulse. This shows that we have many different wavelengths. So it's a long pulse in the time domain, but it's very high energy. So then we propagate this pulse, and then we go into a grating compressor. And what we do is the inverse as we did here, we compress the pulse. Now, the reason why we need to do this is because the coatings in all of these components cannot withstand high intensities. And so we need to transport all this energy, if you will, all this energy through the optics at levels that are below the intensities at which the coatings damage. So this is an example of a petawatt class titanium sapphire chirp pulse amplification laser system that has been developed in our group. And I don't do this work. My colleague Jorge Roca does this work. but we actually developed the coatings for critical components in this shear pulse amplification system. So some of the problems that we are interested in is in understanding if we put coatings in some of the crystal amplifiers, and the crystal amplifiers look like this. They are, for example, in this case, ytterbium YAG, and then on one of the surfaces, we add a coating of an anti-reflection coating, and in the other one, we put a coating that is a high reflection coating. Now, a high reflection coating, the type of geometry that we use is shown here. Again, remember I told you the intensity, the electric field intensity will be very high at the AR coating interface. On the contrary, an anti-reflection coating, the standing wave electric field looks like this. And so notice this is the AR coating interface. This is the substrate coating interface. The intensity is about the same. I mean, it's slightly larger at the AR coating interface, but not much different than it is here. And so this by itself causes issues because now I have high intensity at the substrate coating interface. And as I am going to show you, this is creating problems that is affecting the laser damage behavior of the coating. Now, these crystals in our laser operates in vacuum and at cryogenic temperatures. So we actually tested the components at these conditions. So what we learned from these experiments is that when we test YAG, the crystal by itself, or when we test the high reflector deposited on YAG, we see a behavior. This is the number of shots to damage as a function of the laser fluence. And what you see is that, there is a I would say, a 1/x type of behavior, a hyperbolic behavior. And that shows, okay, if we go with very few shots, the fluence at which I will damage the coatings is higher. And then as I go with many, many shots, the fluence decreases. And it's expected because you have accumulation effect. This is very deterministic. And so we see that in YAG and we see that in the high reflector coatings. Notice here that the damage threshold of YAG is about 25 joules per square centimeter. Of the high reflection coating is about 32 joules per square centimeter. And it's, again, the intensity at the coating substrate interface is very small. So we are seeing here the behavior of the coating and not the behavior of the YAG. When we do the same analysis on the AR coating, what we see is that the number of laser shots to damage is much lower than here. And I mean, and the fluencies are much lower. And so this behavior actually, and it's very, varies a lot. I mean, notice the error bars, they're huge. So the onset of damage is about 10 joules per square centimeter when we have about, 100, or 150 pulses. So what this told us, whenever we looked at this data originally, we said, oh, there's something happening here. And so what we did is we first associated this behavior to the influence of the substrate. And so we sent the substrate to polish to a much better surface roughness. And when we do that and we repeat the experiment by growing an anti-reflection coating on YAG, we see that now it will take a much larger number of shots to damage at the same, at slightly higher fluencies. And this is good news because it's telling us that we don't have to, that the issue is not on our coating, but rather that is on the crystal where we grow the coatings. Another problem that we are working on is studying the laser damage behavior at ultra short pulses. And we do this, these are femtosecond pulses, 10 femtoseconds or below. And we do this in collaboration with Inan Chowdhury from the Ohio State University. And so here, what we are interested in learning, again, are the mechanisms of damage. And so we design specific structures that then we test with pulses that are ultra short, 10 femtoseconds, and 35 to 150 femtoseconds. And again, this is all related to trying to improve the performance of shear pulse amplification systems. This plot is very complicated, but what it shows is actually these are optical microscopy images and atomic force microscope images that shows that when an intense pulse impinges on these coatings, there is a bubble forms, and a bubble forms at the interface between the top silicon dioxide layer and the bottom hafnium dioxide layer. And what you see here, in a sense, is a spring that is doing this. So there is this bubble, doesn't quite lead to damage unless the intensity increases, but it's just, it relaxes back to whenever the laser is off. And so the way to think about it is that you have, a relaxation process, but the damage occurs right here at the interface. So there are lots of opportunities now that we have to actually investigate how we can tailor the materials to increase, laser damage performance. And so we are looking at new materials. We are looking at the role of interfaces. We are looking to provide a stress control. And then in addition, our colleagues are performing modeling calculations that support our work. So I think with that, I want to conclude and just the technical part, and I want to, thank all of the members of my group that you see here. And we also have collaborators in the laser lab team, which is led by Jorge Roca, and as I said, I collaborate with a faculty member at the Ohio State University. The LIGO coatings are some of the metrology that we do is actually carried out at Caltech and at Stanford. So this concludes the technical part of the presentation. Now what I want to do is I'm going to wear my hat of IEEE Photonics Society president, and I am going to tell you about the society. And so the IEEE Photonics Society is a professional home for a global network of scientists and engineers who advance laser, optoelectronics, and photonics technologies for the benefit of humanity. And I can name multiple technologies that have changed the way we do things. And in fact, today we are able to communicate in this way thanks to fiber optics that has enabled massive transport of information at the speed of light. So the Photonics Society engages different groups like yourself, universities, and young professionals, students, through its chapter. And you have formed a chapter, and so you know that by forming a chapter, you have some responsibilities, and then the society supports you to promote, the field, like what we are doing right now. I mean, we have I discussed, some of the work that we are doing. So this is, these are photonics technologies, and so that you will, learn of the breadth of the work that is being done within the society. So how do the chapters do this? Well, we have lectures and workshops like this one. You can also organize regional conferences. And then you can also, have awards or develop, you can also participate or be eligible for awards, scholarships, typically at our main conferences. So right now we are in a situation in which we are on hold with these opportunities, but they will eventually come back. Now, some of the other activities that chapters do is they participate in humanitarian and service projects. And that could be, for example, going to a high school and teaching students, in the fundamentals of optics and photonics. So what we are a society that is global and that it intends to be very diverse. And so we try to reach to every, to as many chapters in the world as we possibly can. And so I am delighted that today I'm speaking to you who are on the other side of the globe. Actually, you are. I have to go like this if I look at the globe, and so it is, it is a unique opportunity because that in the sense that it allows me not just to to present the technical work, but also give you present or discuss with you opportunities that you have for developing your professional career, as well as you learn what we are, the way we work here in the United States. And I will hope that at a certain point, and this is something that we can think about, you should think about, maybe we can do the reverse. Maybe we can set up a workshop in which you give presentations and I will listen, and then I can give you feedback, either on your work or general feedbacks about your professional development. So we are very committed to diversity because we think that the diversity enriches all of our efforts. And of course, we are very committed to improving the standing of women in photonics. And so we encourage young professionals to join. I think this is a very rewarding area of research, and being in engineering is a very rewarding profession. So we have large efforts dedicated to supporting and attracting, women and creating, mentoring women in photonics. This starts at the undergraduate level. It grows into the graduate level for students, but it also goes beyond because we also support young professionals. So don't think that your participation with the society ends when you graduate. No. You will actually continue. We hope that you will continue. And you have to remember that you are the legacy, so you will have to be on the leadership at a certain point because we are going to move away. I mean, this is like a carousel where we start, training you, and then you start rising to the top, and then you will do the same with the next generations. So for young professionals, we have different activities. We have signature events. We have a meet-at program. Actually, I should say that for undergraduates, we also have this meet-at a mentoring program at the conference, and that's how I met Mira. I met her last year at the IEEE Photonics Conference through a mentoring event. I mean, we were paired by the membership, by membership to in the conference. And so we interacted throughout the conference. And all of you will be able to do that in future conferences. If you apply, you have to apply to this. We also have resources. We offer workshops, and especially now we have a series of webinars that I really encourage you to participate because they are on topics that are relevant to photonics, like, for example, using finite element analysis to design photonics devices. And part of what the society does is it also supports professional development through publications. So we have the two main products of the society are publications and conferences. And we have different journals that have a different flavor. The one that is open access is IEEE Photonics Journal. So even if you, if you're a member of the Photonics Society, you can go to the IEEE homepage and look at the content of these journals. If your university has a subscription, you can also do that. But IEEE Photonics Journal is unique in that it is open access, and therefore you can read it, without just going to Google and typing IEEE Photonics Journal. Now, this is one of the advantages of publishing in an open access journal, is that in a sense, everyone has access to the paper. And so your work, if published in an open access journal, will have more visibility. It will have instant visibility. We also have a distinguished lecturer program. And so I encourage you to look at the IEEE homepage and invite some of these invited speakers to your workshops. Right now, because we are going, we are virtual, there are many more opportunities for these distinguished lecturers to join and give a talk like I am doing. So go to the homepage and check who will be available and invite them. You will have to do this with sufficient time to be able to secure one of their presentations. So I want to sort of close this. I think is my last slide by saying that it is extremely important for us that all the work that you do, we count on members and volunteers engagement on the many different aspects. And what is the benefit to you of being engaged in a professional society is that you meet people, number one, and then you learn also how to talk to different constituents, how to sell an idea, and all of that are skills that we need in our profession. So, right now we have again, as I said, we are not able to meet in person. However, we have what is called an e-mentor match program. And this e-mentor match occurs through the web. So I encourage you again to look into this so that then you get the most out of being a member. All right, this is my very last slide. And I am showing you here the beautiful mountains we have in Colorado. And I just want to briefly mention that, we count on you to help us grow, to help us start new initiatives. And at the same time, what we offer are unique opportunities for professional development and for developing soft skills, something that you don't learn when you are in a school. In a school, you are focused on your coursework or on your research. So with that, I would like to thank you for your attention, and I will take questions from the audience.
Thank you, ma'am, for your stimulating and fruitful webinar session. Now, let's move on to the question and answer session. From UV visible spectroscopy, how can I measure optical band gap of titanium dioxide coating?
Okay, so how can you measure optical band gap? The band gap of titanium dioxide is about 3.8 electron volts. And so you can do it in different ways. You can do an absorption measurement. If you have the right, you need a source, a broadband source that will cover the wavelength range where the band gap occurs. Now, the way we do it is with ellipsometry. In ellipsometry, we do have that broadband source. And so we obtain the variation of the extinction coefficient as a function of wavelength. And then from there, we construct what it is called a TOC plot, and we determine the optical band gap. The optical band gap is typically slightly smaller than the band gap of the crystalline material, and that's because there are different defects that reduce the band gap.
Thank you, ma'am. What is the basic difference between nuclear radiation and electromagnetic radiation and their application with respect to cancer patients?
Okay. The electromagnetic. Okay, this is a question that has many different answers and possibilities, because with nuclear radiation, what you're doing is you're accelerating particles to extremely high energies, and then these particles will actually, in the case of cancer treatment, will hit the tumor and will destroy the cells in the tumor. So the way to think about it is that the particles are like projectiles. They will be alpha particles, or it could be neutron, collection just neutrons, and they are like projectiles that hit the tumor and destroy it. In the case of electromagnetic radiation, you have electromagnetic, that you can have electromagnetic radiation with wavelength across the spectrum, and so there are different ways that cancer is being treated, as far as I know, and I may not know all of the possibilities, but one possibility is to use X-rays. And again, the X-rays, you have to focus them to the region where the tumor is, to actually kill the cells, but the process, the interaction is very different than the particles. There are some efforts that I have seen in which people are trying to reduce the size of tumors by injecting a solution with gold particles that concentrates on the tumor, and then a visible laser is used to destroy the tumor, exploiting plasmonic effects. So there are many different technologies that are being developed. I certainly am not an expert in this field, so I couldn't tell you which are the most successful ones.
Okay, ma'am. How can I calculate absorption and reflection coefficient?
That it comes from electromagnetics. So in your electromagnetics class, you use, essentially the way to think about it is, that if you have two materials and I have an electromagnetic wave at the interface, I will generate a reflected signal and a transmitted signal. And then you have to combine the effect of transmission and reflection at multiple interfaces. And so that is done using matrices. So you typically in your electromagnetic class, you only calculate this for a single interface, but you can do it for multiple interfaces. So that is plain electromagnetic theory.
Okay, ma'am. Which is the best optimizing technique to reduce damage?
Oh, that's a good question. Right now, what we are doing is in coatings for ultra short pulse laser, we are carefully choosing the high index material to be one that has the largest band gap. Silicon dioxide has the largest band gap among all the metal oxides. And so silicon dioxide is the material that will have the highest, laser damage threshold. And so we use, high laser damage threshold materials essentially.
Okay, ma'am. The next question is, how can I calculate film thickness and refractive index without interference fringes?
Okay, there are models to calculate refractive index. This, for example, there is a model that is called the Cauchy model. And the way to think about it is that the refractive index is modeled using a classical oscillator. So you have the atom. Your valence electrons, when an electromagnetic signal, start to oscillate with the field, but the electrons will actually have also a natural frequency of oscillation. So that's how we model the electric field. That's how we model the refractive index as a function of wavelength. You can also, using Kramer-Kronig's relationship, obtain the extinction coefficient using the classical model. So from the refractive index, you can actually calculate the extinction coefficient. But to calculate the absorption, you need to involve quantum mechanics, because that depends. Now you need to have absorption, you need to have two levels that are resonant with the wavelength or with the photon energy.
Thank you, ma'am. Now it's time to express our gratitude. On behalf of the Department of Electronics and Communication Engineering, St. Joseph's Institute of Technology, St. Joseph's Group of Institutions, I thank our guest lecturer, Dr. Carmen S. Menoni, for this enthralling speech on optical coating. Thank you, ma'am, for taking out time from your busy schedule and joining us to share your knowledge. I would like to extend my gratitude to our chairman, Dr. B. Babu Manogran sir, and our managing director, Mrs. B. Jessipriya ma'am, and director, Mr. B. Sashekhar sir, and our principal, Dr. P. Ravichandran sir, for giving this great opportunity to conduct this workshop. And special thanks to our department heads, Dr. C. Nyanakausalya ma'am, Professor and Head, Staff and Student Affairs, and Dr. G. Rogini ma'am, Professor and Head, Lab Affairs, for their support. I thank each of our staff coordinators and the organizing team for arranging this webinar successfully. And finally, my sincere thanks to all the participants for your active participation and support. Once again, a big thanks to Dr. Carmen S. Menoni for your presence. Thank you all.
Thank you very much for the opportunity, and I look forward to meeting you in person, but if not possible within the near future, to have another one of these webinars or workshops. Thank you.
Thank you, ma'am.
Thank you,
Bye.
Dr. Suman. Thank you. Thank you for the informative session.
Oh, you're welcome. Nice questions. Very nice questions.